So this is the second video for circular motion, and in this video we're going to look at a couple different example problems. So these are typically pretty close to the ones we do in my class, and pretty much I'm going to go with drawing a picture and just talking my way through the problem. So let's assume that we have a circular disc. And let's say that it has an initial angular speed of 0, so the disk is not moving at all. And then let's say after 2 seconds, the disk has a final angular velocity of positive 3.5 radians per second. So in this problem with the positive sign, it means that we're actually spinning counterclockwise. And so if I were to draw a line on here, after 2 seconds, this disk would be spinning 3.5 radians per second, which is almost 1/2 a rotation. Because remember that half a rotation is 3.14 or pi radians. And so we know that it's about a half a rotation every second. And we are going to be looking for the angular acceleration, and also we are going to be looking for the amount of degrees, or we could just look for the amount of radians that have taken place in 2 seconds. So basically I'm asking is how much did this rotate in 2 seconds? Okay, now this could be talking about a merry-go-round, a wheel on a car, anything like that that started from rest and maybe somebody pushed it or somebody steps on the gas. And so when I look at my 3 variables that I have, it leads to the first kinematic equation for circular motion. And that one was right here. So we have our omega f equals omega I plus alpha t. So the angular velocity equals the angular acceleration times the time. Our initial velocity was 0, and so we are going to just solve for, I made a little mistake there, we are going to solve for the alpha, or the acceleration. And so that would be omega f divided by t. And if we put our numbers in, that would be 3.5 radians per second divided by, 2.0, and so it's a half. And we have 2 significant figures. So it'd be positive 1.75? 1.8 radians per second squared. Okay, so that's our acceleration. And we're going to be looking for theta. Now the truth is when I do these problems, I do not like to use things we solve for. So your first instinct would probably be to use this. Which is our third equation. It's the longest looking one too. But students like to use it because it's already solved for theta. I don't think it's the best solution for this. Okay? So we're going to use the second one. And the reason I'm going to use it, and I'll write it over here, the reason I like to use that is because, look, we solve for alpha. Ooh, I still have it. I guess there's no way of getting out of it. Okay, so it's up to you. What do you want to pick, this one or this one? All right, you should get the same answer. Okay, now we're going to solve for theta, which is the displacement. It's how many degrees have rotated in those 2 seconds. Right. Now we have two equations left. And when it comes down to using them, I don't necessarily like using either one of them because they both involved alpha, but in this case we have no choice. So we're going to solve them both ways, okay? And let's just see how it works out. So the first one that you're probably inclined to use is our third equation, which deals directly with solving here for theta. And so we would put in, what do we got? 0, 1/2, alpha is 1.8. See, you got to make, don't make that mistake. I put meters. Radians per second squared times our time, which is 2.0 seconds squared. All right. So 2 squared is 4. Half of that is 2. 2 times this is 3.6 radians. All right. Now, if you notice, doesn't that look like this number right here? Don't think you did something wrong, okay? You didn't. All right, now let's go ahead and solve it using the second equation. Okay, and so we're going to solve for theta. Remember that omega I, the initial angular velocity, is 0. And so we get the final velocity divided by 2 times the acceleration. So we have 3.5 squared divided by 2 times our alpha, which is 1.8 radians per second squared. Use my calculator here. 3.5 squared divided by 2 divided by 1.8. And amazingly, we get 3.4. So here's a question. Are those numbers the same? Is this number and this number the same? The answer is yes. Okay. It's the great thing about physics and rounding. This right here was 1.78. I'm sorry, 1.75. Okay, we rounded it to 8. That ended up causing us to get a little bit higher number. But regardless of how you do it, either one, it's the same answer. Okay? Now let's look at another problem. Okay, now let's do another problem. We're going to do it pretty much directly from one that we've used in class. Okay, now let's do another problem. This is going to be pretty much like one we did in class. And if you can remember this, the old floppy disks that go into computers, and if you don't, just look it up. They're crazy. They were small as far as how much memory they held. And it was a great thing when you went to CDs. rewritables because you could hold so much more information. But even those had problems. But let's say you had a floppy disk. When you put them in, they go clunk. And let's say that the floppy disk spins an object with an angular velocity of 35.0 radians per second. Okay. And let's say that this takes place in a time of 0.89 seconds. All right. Now it says, what is the angular acceleration? Okay. So we're looking for the angular acceleration. And so when you put that disk in, the one thing you have to remember is that the initial angular velocity would have been 0 because it would have just started out not moving. And so this number right here is actually, I'm going to write it on the other side, omega f. Right? Now, does that look exactly like the previous problem? Absolutely. Okay? And you're going to notice that a lot of these problems look exactly the same. Okay, let's look at another problem. Let's say you have a car. I know students love my cars. Look at that thing. That is great. Let's say it's moving in this direction. If you think about it, how would those tires rotate? They'd probably rotate this way, correct? Turning this way. Sometimes it's hard to think about that when you're just looking at the picture, but that is true. So actually, we would have a negative angular velocity, okay? Because we'd be moving clockwise. And if you look at the first video, I went over about positive and negative, okay? So let's say it starts out with an initial angular velocity of negative, how fast could it be rotating? How about 75.6 radians per second? Okay. That'd be the tire going around, I don't know, like 11 times, 12 times in 1 second. That's probably pretty fast, and maybe that's ridiculous, but let's say that's it. Now the person steps on the gas, okay, in the car, and that causes an angular acceleration, let's say, of negative 3.56 radians per second squared. Okay. Now, why is this negative? Well, if it was positive, that'd be going against the wheel and actually be slowing down. So these have to be in the same direction if you're speeding up. Right. Now, let's say that takes place over... How long would somebody be standing on the gas pedal, stepping on the gas pedal? Maybe 3 seconds? And I want to know, what is the final angular velocity? So let's take a look. We have Wi, omega, we have alpha, we have the time, Wf. Once again, we're going to that first equation. If it seems like we're using the same thing over and over again, guess what? We probably are. There's only 3 equations. Okay? When we solve for that, we're not going to cross out omega I this time because it does have an initial velocity. Oop. You're going to notice that you're going to probably do the same thing I'm doing. We're so used to using meters all the time that when we go to do these problems, the traditional or the normal kind of thing that we do is just go ahead and put that in. So we have negative 75.6 radians per second, and then we're going to add to it a negative 3.65, running out of room, and we're going to multiply it by 3.0 seconds. Okay, so we're going to multiply that all out and add it. And that gets us to 86.55 radians per second. If we look at that, it's two significant figures, so it'd actually be 87, negative 87 radians per second. So how do these units work out? Okay, let's just look at the units. So my 75.6 is radians per second, plus my alpha is radians per second squared, and my time is just seconds. So this would cancel the seconds out, and we get radians per second, which we add up. Right? Now you notice how I said over here that this 75.6, I said that's about 12 times around in 1 second. And that seems pretty fast. You know, in later videos, when we go over tangential velocities and stuff like that, if I remember, we can go back and we can determine if this is actually really maybe realistic. Okay? And it's actually a pretty simple equation to do. But I think we'd have to maybe go out to a car and actually measure the radius of the tire. So anyway, these are two pretty simple problems, and we could go ahead and solve for theta if we wanted to, but you're going to notice that these are the same exact things that we were just doing for the regular kinematic linear equations.